Now there's 5 slides. First one.
Okay. Our projector is also being a little bit affected by the weather. Kind of sleepy today. All right. Get started for this week. Unless anybody has questions about the test. Yes, I'll have it graded soon. I think I had mostly done. Have it back to you soon. But does anybody have questions about it? Okay, I guess we'll have them once I'm done. Okay, so our outline for this week, and I hope to do the first 3 topics today, then the next 3 topics we'll get somewhere hopefully along in that by the next class. So we are going to expand from a single qubit, which is all that we've been discussing so far in this course, to multiple qubits. So let's expand into the universe. And the joke, of course, over here is that ideally, in physics, typically we talk about things, we go from 1 to n and we generalize like, n equal to infinity in thermodynamics or something like that. But like in quantum mechanics, like 2-body problems is probably all we can do on paper or by hand. And beyond, like, say, n equal to 3, things start to get complicated. And so for our discussion, most of the time we'll be talking about 2 qubits. Occasionally, I will write down some 3-qubit states just so you see how it's done. But for most of the discussion, we'll be talking about 2 qubits. Okay. So n will be 2, at least I can promise you in this part of the course. And as we get to higher orders, we'll have to resort increasingly to computer codes, and then eventually, of course, to actually writing it on a quantum computer and seeing what happens then. Okay, so for multiple qubits, we're going to write their states using something called the tensor product state, or the tensor product operation. So for example, 2 qubits which are in the state 0 are written as 0 tensor 0. Okay, so you should think of the 2 qubits as, say, the physical qubits. When you think about them, have that sort of mental picture in mind. You might have 2 electrons, right? One with spin up and one with spin down, for example, right? You've seen that example in the articles I've shared with you, that a qubit can be an electron, the spin of an electron, or a spin of a nuclear spin, or it could be a photon, or it could be a superconducting qubit, and those have various varieties of qubits as well in them, realized through various configurations of superconducting elements. But you can think of it as like, okay, there's a qubit here and a qubit there, and these 2 live sort of in different Hilbert spaces because they're in different, say, positions, for example. Okay. If it's photons, it might be because they occur at different moments in time, so on and so forth. Okay. So everything else remains, the description in the qubit basis, this confused me when I was first learning about it, but in the qubit basis, these 2 states look identical, 0 and 0. So what's different about them? There are other degrees of freedom that we're not writing down explicitly, but that are different for the 2 qubits. Like, say, the position on the chip, or their position in space, or their momentum, for example. So all of those are different. That's why we can separate out the 2 qubits. Okay. So we'll compress this notation 0 tensor 0 to 0 0 like this, or even more compressed notation, which is most commonly used, is just ket 0 0. Okay. And it's understood, and we'll come to some conventions about how we write these strings of digits, the binary digits. So this is a 0 0 binary digit, 2 bits basically. And we are writing that, we are using that to represent this tensor product of two kets, which are both in the state 0. Okay. So the possible Z basis or computational basis state for 2 qubits then are pretty straightforward. It's either 0, 0, 0, 1, 1, 0, or 1, 1. Those are the only four possibilities for the Z basis states. And each of those, you should think about them as 0 tensor 0, 0 tensor 1, etc., etc. And the most general state will then be clearly a superposition, as we have learned already for single qubits. Okay, so we have complex coefficients C0, C1, C2, C3. Okay, and those are all going to represent the most general state. Those numbers are going to represent the most general state of the basis of the qubit. Okay, and of course, the probability of measuring the qubits in either the state 0, 0, which represents a measurement where the first qubit gives you a 0 and the second qubit gives you a 0. That's what the 0, 0 measurement would be. The probability of that occurring is just norm squared of C0. So C0 squared, okay, complex number, the norm squared. Okay, same thing. The probability that I'll get the left qubit to be 0 and the right qubit to be 1 is C1 and C1 squared, C2 squared, C3 squared. Okay, modulo norm squared. Okay. And the sum should, of course, equal to 1 for normalization. It has to be found when I measure the 2 qubits, it has to be found in one of those states. Yes.
C1 and C2 equal, like the 2 qubits, and there's no difference. How to find which one's the left one, which one's the right.
Well, as I said, they have other degrees of freedom that allow us to differentiate. So we know, for example, that qubit 1 might be in position A, qubit 2 will be in position or 0, the labeling, whatever. But one is in one position, the other is in another position. Or the photon, one occurs at one time, the other occurs at another time, or has some other degree of freedom that differentiates. So we do, in fact, have to decide 0, 1, or 1, 0. Those are different basis states. And okay, we can also write it for 3 qubits, right? It's just exact same procedure, 0, 0, 0, 0, 0, 1, up to 1, 1, 1. And now we introduce sort of an even sort of compressed notation for this using our knowledge of binary digits. Okay. And so the idea is very straightforward. We know that the binary string 0, 0, 0 represents the decimal number 0, right? 0, 0, 1 represents the decimal number 1. 1, 1, 1 represents the decimal number 7. Okay. So we can write the Z basis state of 3 qubits as ket B2, B1, B0, where B2, B1, and B0 are binary digits. So they can only be 0 or 1. Okay. So we labeled the right qubit. Notice that the rightmost qubit, I labeled that as having the least significant bit in the binary string. The middle qubit, of course, is the middle digit. The leftmost qubit is the second bit in the binary string. So that decimal representation of the state, this is just a convention. Okay, it's just a way to label the states in a more compact notation. Okay. And so for like 3 qubits, it's not that difficult. We can write down 0, 0, 0, 0, 0, 1, etc. But imagine you go to 100 qubits. Or of course, eventually we would hope in a quantum computer to get to thousands of qubits, right? It'll be difficult to keep representing them as binary strings. Okay. So here is the decimal representation of that same state is just simply take those binary strings and convert them to a decimal number using the standard, technique or standard way in which we convert binary to decimal. Okay, which is just that. Okay, we can this convention that I just told you about, where the rightmost qubit is the 0th bit, which is the LSD, least significant digit for the decimal representation. It's called little endian. And if you know a little bit of computer programming, then you know about this when you have had to deal with anything in memory. If you are actually like accessing it, different compilers will represent the numbers, the floating point number, with different notations. One is called big endian, where the least significant bit is the first bit in that string. Okay, and the other one, and this is little endian, where it's the rightmost bit in the string. Okay, and little endian is a format in your book, and also I think in the IBM. I have to check, I have to double check that. But for example, there are other textbooks that you'll see if you start picking up a more advanced text, which is called Nielsen and Chuang, that I wrote down in the initial, like resources. They use the big endian format for the binary representation. Okay, it's just something to be aware of, that you need to know this. And of course, every compiler, you should know what its notation is for these states. Yes.
Is there a reason for the different preferences, or is it just
you just pick.
Okay.
Yeah, I think it's all about, it's the same reason why, I forget which one, but I've dealt with this myself. I'm trying to think where. I was programming, for example, I think I was programming an arbitrary waveform generator, and it's just the way that it reads the data from the memory was big endian. So when it takes a data point from the memory block, it converts that number to a decimal number using big endian format. So I have to make sure that when I write the binary string to its memory block, I have to make sure that that binary string is correctly formatted so that I get the number I want out. Otherwise, I'll get the wrong number out from that instrument. It's the same with compilers. It's the same, and I'll make sure to double check what our IBM compiler uses as well. But yes, what is it?
so? Yeah, just to go off of that.
Yeah.
I know a lot of classical computers use big endian as the standard.
Yeah, exactly.
Architecture.
Correct.
Big endian
Correct.
nowadays.
Correct.
Do you think that
Right.
in the future they'll urge to?
No, this is just a notation in our textbook. I have to double check what the IBM compiler uses. I'll make sure to double check and let you know. But this is our textbook, and I wanted to follow the textbook, so I'm using that format. It also kind of looks standard notation, right? I mean, I write 0, 0, 0. Our mind is by now hopefully is trained to think of the last bit when we write it down, the rightmost bit as the least significant bit, and the leftmost as the most significant. That's how we've been writing it. For example, when we did those conversions when we did the binary logic part of the course. So following that same approach, we are keeping it in that same convention. But as you said, modern compilers a lot of them are using the big endian. So are a lot of other things. And I need to double check the IBM citation. I'll let you know what that was. Double check. Okay. Anyway, so the idea is now instead of writing those C0000 plus C1001, I just write this as 0 through 7. And now it's understood 0 through 7. You should immediately know by now that means it's a 3-bit string, and that it's 000 up to 111 that we are representing by the short form notation. Okay. Yes.
We do this with higher qubit states.
Yeah, I'm just going to show you that again. Okay. And so we can see that writing a column vector C0 through C7 of these complex numbers will keep track of this thing. It's just a statement that you already probably figured out from the earlier equation, but it's now more hopefully obvious. We just number them 0 through 7 from top to bottom. 0, 0, 0, 0 at the top, 0, 0, 1 next, and then down to 1, 1, 1. That's the C0 to C7. I'll introduce that part in a few slides. Okay, so to answer your question, with n qubits, so now there are capital N equal to 2 to the power n basis states, right? That's just binary conversion of binary string to a decimal number will give you 2 to the power n Z basis states, which we label as the n bit strings 0 up through n minus 1. So 0 up to 2 to the power n minus 1. So a general basis state will be written as, again, same idea. I take 0 up to the n minus 1 binary digit, right? So that's the binary digit, small n minus 1, because it starts at 0 numbering. So I have to go up to n minus 1. And then when I convert it to the decimal representation, I use our little endian format. I take 2 to the 0, B0, 2 to the 1, B1, up to 2 to the power n minus 1, Bn minus 1. Right? Everybody okay with that? And I should tell you now, please, if you're following along with your textbook, there's an error in your textbook here in this equation. Okay. So make sure to correct your version of the textbook if you're looking. So the most general, the author basically writes 0 up to capital N minus 1, which is an enormous number of states, because that's 2 to the n, which is enormous. So yeah, that would be totally wrong, or totally impossible to keep track of, I think. Anyway, so C n minus 1 up through, coming back to this, the summation j equal to 0 up to n minus 1, C0 plus C n minus 1 ket n minus 1. Okay, so that's now our compressed, even more compressed notation. So you see that there are n elements in the column vector, 0 up to n minus 1 in the column vector, which I will produce as well in a few slides. Yeah, and now this brings us to the often something that you'll hear a lot in like popular media articles that talk about quantum computing, when people are just trying to like explain, why quantum computing is powerful, right? You might have heard this. Okay, so we have n qubit states, right? Which, as we just seen, requires 2 to the n complex numbers to describe, right? The C0 up to Cn minus 1 that I was just showing you, that's capital N number of complex numbers, capital N is 2 to the power n. Okay. So for n equal to 300, this will take 10 to the 90 numbers. Okay, just 2 to the power 300, which is greater than the number of visible atoms in the universe. Okay. So I think it's 2 to the 10 to the 90, but anyway, it's on the order, it's much bigger than the number of atoms in the universe, or visible matter in the universe. So that's what people say the power of quantum computing comes from this. Look at that. In your quantum computer with just 300 qubits, you're computing the entire universe, or you could compute the entire universe, is the claim. And that's what they call quantum parallelism. Okay, because in parallel, everything is being computed, together, and wow, this is enormous amount of computational power, right? Wrong. Okay. And there's a great comic, Saturday Morning Breakfast Cereal, and they have like this really awesome. So just Google Saturday Morning Breakfast. I hate their website because they got so many ads on it, but it's a great comic. It's about quantum computing. Okay, and it like really does a good job of like it was co-authored by Scott Aronson, who's a famous quantum computer scientist, and which you read one of his articles for the beginning assignments in Scientific American. So the important thing for you to understand is quantum computing isn't just a matter of trying all the answers in parallel. Okay, that's very important. I hope you when you come out of this class for sure you should understand that. And the reason is, yeah, there are exponential number of amplitudes to track, but it's not clear that we actually are using all of them, okay, in the quantum computer. Because nobody can actually go in there and see, we can simulate, we can try to understand the power of quantum computing, but we don't really know that we need all of the 2 to the n complex numbers in the actual calculation of whatever problem that you're trying to solve. And we just don't know, okay, whether that's needed or not. It could be that in the end, there's only a polynomial number of complex numbers that it's actually tracking inside the quantum. Okay. So, and also then don't forget, we are projecting, right? We project our results onto one of the basis states, right? We always have to make a measurement at the end to get some information out of our quantum computer. So we collapse that entire huge state into one of the Z basis states, correct? We hope we've set up the algorithm so that our answer is somehow encoded into the right basis state so that the final answer we get will give you the answer to the problem you're looking for. But, in the end, that's it. That's the answer, right? That's the one number that you're going to get out of the calculation. So, we must take this whole claim of quantum parallelism with a grain of salt, a big grain of salt. We suspect, of course, that BQP, which we have introduced in the computational complexity class of, bounded error quantum polynomial time problems, we suspect that this class contains polynomial P. We suspect it. We have problems that we think are in BQP but not in P, right? We've talked about that, but we have no proof that that is indeed true. And so that would be like a big advance if we were actually able to even show that. Okay. All right. So that is just a little aside, just to warn you, please, whenever you hear that, just know that that person might be just saying it so that, it can be a media type of thing, like, popular science, whatever, but serious people in quantum computing don't claim that, don't talk about it. Okay. All right. Okay, so another compactness notation. So sometimes instead of writing 0 tensor 0 up to 0, we might write 0 to the power tensor n again, or even sometimes, let me see if I can just write it here. Pen, not very good with this pen. Sometimes you might even see 0 to the power. And I should have used small n. Sorry, this is small n because there are only n bits, small n bits. Okay, so this is 0. Sorry, I missed that. Okay. 0. Small n. 0 to the power n. Okay, that's another notation. And of course, we can also write the dual vectors, the bra vectors, with the same notation. So it's bra 0, tensor with bra 0, tensor with bra 0 is also 0. Okay, yeah, replace that capital N by small. Okay. And yeah, so we can simplify the bra notation. You can see how that must go. It's 0, tensor n is just bra of 0 up to 0, and so on and so forth. Okay, so the bra notation just goes like the ket notation, exact same thing. Okay, so we know how to write bras and we know how to write kets for these n qubit states. So of course, we must know how to take the inner product, because as you know, a lot of the things we do in quantum computing, in quantum mechanics, are obtained by taking some kind of inner product of states with each other. When we do a measurement, we are taking inner product with that particular computational basis state, the projection of the state onto one of the states that we are interested in. Okay, and so the basic thing to remember is we must always match up only the states for the same qubit. Okay, so here's what I mean by that. So 0, 1, this is the bra 0, 1, and this is the ket 0, 0. When I take the inner product, when I sandwich those together, I must take this 0 and match it up with this with this 0 over here. So these left two bits or states. So that's 0, 0 over here. And similarly, the right states with the right state. Okay. Again, this is, think about, they have separate physical locations or some other property that distinguishes them. So when we take the inner product, the ones only that live in the same state or the same space, so to speak, the same degrees of freedom will overlap with each other. Okay. So that is this state over here. You can clearly see that will be 0 here because, this one is 1 for the left qubit, but this one is 0 for the right qubit. And therefore, this combination 0, 1, 0, 0 will be 0. Okay. So 0, 1 is orthogonal to 0, 0, and also, as clearly obvious, is also orthogonal to 1, 0 and 1, 1. Okay. And you can check that those are all also orthogonal to the other states. Okay. And they only have a unit normalization to themselves. So meaning 1, 1 with 1, 1 will give me 1, and the rest will all give me 0. Okay. So let's do an example just to make this even more clear. Oh. That's nice. Why didn't we get invited to the pizza? Plus minus 0, 0. So by the rules, we must match up the plus state with this guy, the minus state with this guy. So this is plus 0 and minus 0. And plus is of course the state, which is 1 over root 2, 0 plus 1. And now with 0, and then times 1 over root 2, 0 minus 1, oops. Again with 0. So clearly the only thing that survives is this pairing over here and this pairing over here. These two go to 0. Okay. So that means I get 1 over root 2 of 0, 0 times 1 over root 2 of 0, 0, which is just 1/2. Okay, easy enough, right? Everybody follow that? What would have happened if I had put 0, 1 over here? So instead of 0, 0, if I put 0, 1, what would happen to the same thing? Okay. Yes?
To be negative.
Negative 1/2. Very good. Everybody follow that? It's just a minus sign from here that we have to take into account. Okay. Yes.
We break down what you did to get from that second line to the third line.
From here to here?
Yeah.
I just wrote the states plus and plus over here.
Oh.
Yeah. So a plus is just 0 plus 1, root 2. And again, plus, this is minus, so that's 0 minus 1 divided by root 2. Okay. And then take the inner product. Inner product is linear. So since it's linear, I can just take it inside this sum. And this one vanishes and this one vanishes. Okay, so that's our simple example, but it basically tells you how this is going to work for all the more complicated cases. Okay. All right, and now we will introduce so we have done the ket algebra version. I just showed you how to do it with kets, right? By writing out the kets and writing out the bras and doing the inner product by hand on the board. But as we have learned in the last few lectures, there is a more compact and more useful representation of ket algebra, which is called linear algebra, right? And we learned about how to manipulate things with linear algebra, the same kets and bras that we manipulate by ket algebra, we can also manipulate them by linear algebra. And so we introduce the linear algebra representations of the kets, which is the column vectors. And we introduce a new thing, which is a tensor product in ket algebra is equal to something called a Kronecker product in linear algebra. So if you know linear algebra, then this will be, hopefully more obvious to you, but don't worry, we'll introduce what Kronecker product means in just a minute. But that's what the equivalency is between tensor product in ket algebra to the Kronecker product in linear algebra. So if I write the state 0, 0, okay, the same ket state that we wrote for a 2-qubit state, then we know in linear algebra it's a column vector, 1, 0, and this is another column vector, 1, 0. And I want to take the tensor of those two, which I will now do using the Kronecker product, which is just very straightforward. We just use the rules of linear algebra. We take this 1, 0 state and we multiply out into this guy over here. We take the 1, 0 state and we multiply out into the 0 state over here. Okay. So it looks very much like the outer product that we introduced last time, except now it's a product between two column vectors. In the outer product, we were typically doing between a bra and a ket. Okay. Here we're doing between two kets. Okay. And so that's why instead of getting a matrix, when we did the outer product of a ket and a bra, we got a matrix. Here we're getting a bigger column vector. Okay. But it's the same idea. Okay. We just take this and we put it in there in the first spot and multiply it out, and 1, 0, put it in the second spot here and multiply it out. So clearly that is just going to give me the column vector 1, 0, 0, 0, right? Just multiplying the ones in there and the zeros in there. So that is the representation, the linear algebra representation of the ket 0, 0 in a column vector. And we can do that obviously for the other states. So 0, 1, okay, is 1, 0 tensor with 0, 1, which is the Kronecker product. So now I take the 0, 1, I take it into this column vector. So it's 1, 0, 1, 0, 1, and 0 times 0, 1. So now I get 0, 1, 0, 0. Okay. And obviously then the states, the other two states, so 1, 0 will be the column vector 0, 0, 1, 0, right? And 1, 1 will be the column vector 0, 0, 0, 1. Is that okay with everyone? What I mean by that? And then if I now take the most general state, so C0 times column vector 1, 0, 0, 0, plus C1 times column vector 0, 1, 0, 0, C2 times column vector 0, 0, 1, 0, and C3 times 0, 0, 0, 1, adding them all up together, I get a column vector which is C0, C1, C2, C3. So the Kronecker product of two kets, or the most general ket, is of 4, or I don't know which way you want to call it, columns, 1 column and 4 rows. It's a matrix or a vector, whatever you want to call that, which we just write in this way. Okay. So we are expanding the dimensions of our Hilbert space, right? Qubit was 2 dimensions. 2 qubits is obviously now 4 dimensions. Okay. And that's why we have a 1/4 matrix over here, or 1/4 column vector. Now, you may be wondering, I don't know if anybody's thinking so far about this, but remember, we spent a lot of time on something, some representation of qubits, something that was visual. What was that called? Yes.
Block sphere.
The block sphere. Very good. Excellent. Thank you. Thankfully, you haven't forgotten it all as soon as the exam got over. Okay. Then you may be thinking, surely I'm going to introduce this representation, a visual representation of this 2 qubit space, right? That would be nice. I'm so sorry that I can't do that. It's just beyond our human capabilities to visualize something, because now we have, like for 2 qubits, for a single qubit, as I showed you, we were able to finally get away with representing it by 2 numbers, theta and phi, for example, right? In the block sphere. The 2 real numbers. So that is just like a 2-dimensional space. Yeah, it was a curved space, right? It was on a sphere, but otherwise it was no different from a map or a plane or a Cartesian coordinate or whatever. The problem with this 4-dimensional Hilbert space is now each of these is of course a complex number. So that's 8 real numbers already that we have to represent. Plus, okay, we have some normalization conditions. So that's going to help us. That's one number we can get rid of. And we also have the global phase condition. That gives me one more condition that I can get rid of, right? We can extract a global phase out of these numbers. So that's 2 conditions, but we have 8 real numbers. So that still leaves me with 6 real numbers that I have to represent some. And even if I come up with some clever techniques, that's too many dimensions for our puny human brains to handle. Okay. So as far as I know, I mean, I think I've seen some papers by people who claim that they have a nice representation of 2-qubit spaces. And at some point I should read them more carefully, but it didn't seem to me that better than just writing down the numbers. Okay. So unfortunately, we can't really represent the state of this 2-qubit space. And I may be wrong. Maybe this representation is actually interesting. I had to do some more work on that and let you know. But as far as I know, nobody really thinks about visually what is trying to represent these 6 numbers into something more easy to follow. I know there are things like quaternions and other types of representations. Some of you may be familiar with, other representations of vectors and so on. And, so there are some thoughts about maybe we could use one of those higher order representation, octonions, things like that. But as far as I know, most people just say, okay, you give up, you work with the numbers and don't think too much about I think if we could imagine and visualize those things, I have a feeling that could provoke a lot of breakthroughs because, a lot of the ideas for quantum computing, the single qubit gates and stuff that came about by visualizing the movement of the block of the state on the block sphere. But we have no good way to start to visualize the states that can arise from these 4 complex numbers. And maybe that's holding us back in some way. And of course, you imagine you go to now n. Yeah, now it becomes, exponentially harder to visualize anything. Okay. So anyway, so that's the unfortunate situation that we're in. And we just have to live with, writing down sets of numbers. And this, of course, is then pretty much calling for computer programs that you start using to manipulate these numbers and so on. Okay. And so I just wrote down the most general 3-qubit state. So again, now, as we just introduced, the most general 3-qubit state is j equal to 0 to 7, Cj ket j, where this 0 through 7 represents the 3-bit string, 0, 0, 0 up to 1, 1, 1. Okay. And then again, by the same idea, if you find the linear algebra equivalent, now I have to take tensor of 1, 0, tensor 1, 0, tensor 1, 0, right? That will be an 8 row column vector, right? So C0 through C7 will then represent the most general state for a 3-qubit for a 3-qubit state. That's the most general 3-qubit state. That's just taken by tensor or Kronecker product of the column vectors for each of those states. Okay. And the n-qubit state, by analogy, becomes then just, a column vector with n equal to the n elements, C0 up through Cn minus 1. You can already see for computer code, this is going to become a problem very rapidly. Okay. I mean, representing maybe 2 to the n column vectors, 2 to the n numbers, complex numbers in a computer is maybe not impossible. But with 300 bits, that's still only, 2 to the 300, which is fine, right? But as soon as you start thinking about matrices, which we will introduce in a minute, in a few, not maybe minute, but maybe next lecture, now you're exploding the number of elements that you have to consider. Okay. Okay. All right, and to round out what happens with the bra vector, because we introduced the ket vectors and their Kronecker products, to complete the story, okay, it's the same story with bra vectors. That's it. Okay. So bra vector 0, 0 is just taking the bra vector for the 0 state, which is the 1, 0 row vector, Kronecker product with the 1, 0 row vector for the other one. So that's just 1, 0 tensor 1, 0. And then by the rules of linear algebra, I just take that into each of these elements in the row vector. So that's 1 with this row vector and 0 with that row vector. So pretty straightforward. To see, it must just be 1, 0, 0. So it's basically taking that column vector I wrote for the state and turning it on its side. Okay, it's a transpose, if you like. Okay, that probably was not too surprising. Of course, things you have to be careful if there are complex numbers involved, right? You need to make sure when you take the bra, you do the complex conjugation as well. That's something to keep in. Okay, so as I said, it's often just useful to just write down in code, right? Using the so confusingly, you might sometimes see in different coding platforms Kronecker product is called the outer product, which, it's kind of like the outer product, but in linear algebra representation, we have to be careful. But luckily, both NumPy and Mathematica, this is correctly implemented in the cron and Kronecker product functions. So I just showed you here, I just took, I didn't go through too much of the Mathematica code. I can put it up again on the website. But here is you take two matrices in Mathematica, A and B, and you take the Kronecker product of them, you can see what's happening, right? So it's 1, 2, 3, 4, and then it takes 1 and multiplies it by the entire second matrix B here. So that's 1, 0, 0, minus 1. And then similarly, it takes 2 and multiplies out over here, 3 over here, 4 over here. So it forms a 4 by 4 matrix. Okay, whereas the outer function in Mathematica will give you something that looks like this. So it's almost the same, but it has extra braces and things like that, which makes it harder to deal with. But luckily for us with Python, it's much easier. So I just demonstrate again for simple matrices first, so that it's easy to understand. So A is over here, and then that's just an array, 1, 2, 3, 4, right? Just simple. And then B is just the same array, which is 1, 0, 1, minus 1, I guess I took in this case, instead of 1, 0, 0, minus 1. I don't know why I did that, but anyway, sorry, is 1, 0, 1, minus 1. And then what we get is that when we multiply out the Kronecker product, we get exactly what we would expect. Okay, so it takes 1 and multiplies out this entire matrix, so 1, 0, 1, minus 1, and then 2 times that entire matrix, 2, 0, 2, minus 2, 3, 0, 3, minus 3, 4, 0, 4, minus 1. Whereas if you did the outer product, you get something that looks quite different. Okay, you see that matrix is not the same as the first one. Okay. Okay. And so now we can take our kets that we defined in the last couple lectures when I was showing you the same code. I defined all these kets. And if you look back at the slides, you'll see them. So 0 is just the column vector 1, 0, and so on. So now I can define the same thing, the Kronecker product of the 0 with the 0 itself. And that gives me exactly what I just wrote for you, a column vector 1, 0, 0, 0. Okay. And similarly, you can do ket 0, 1, I can do bra 0, 1, bra 0, 0, bra 0, 1, etc. Okay. So that gives me the same things, but now expanded to the 4-dimensional Hilbert space or the 4-dimensional linear algebra representation. Okay, I guess, I've put it all up here, but again, you can find the inner product using V dot. V dot takes the complex conjugate. So it's good to use that because it automatically takes complex conjugate when it takes the multiplication of two arrays. Here I'm doing taking plus and finding its Kronecker product. You can verify all these by hand. I encourage you to do that because it's never good to just blindly trust the program. Maybe you made a mistake when you were entering it in, etc. So you always, especially at the beginning when we're learning how to do these things, it's always good to double check by hand that these results are what you expect. Okay. But we just verified, for example, the plus. This is plus plus with 0, 0, okay? And this is 0.5, we just saw, and here is plus minus. This is the one that we just verified. So plus minus with the state ket 0, 1 gives me minus 0.5, which we were just talking about a few minutes earlier, okay? So that verifies that indeed it's taking the right product state or inner product. And then we can take any general qubit state. So here is Kronecker product of a general state. So I write down, sum A times 0 plus B times 1. I chose one that I had earlier defined in this Python notebook. And then I take the Kronecker product with itself. Okay. And okay. And the nice thing again, as I said, is, you can find all of these Kronecker product of the bras, and then you can take the inner product of the two states. So obviously you would expect that if you take the same kets psi psi and take its inner product with its bra, which is bra psi psi, so those are both 1, you should get 1, and that's also verified over here. Okay. So yeah, so this is all nice. It just produces the the output that we expect. And okay, so this is, I did an exercise from your textbook, which is it wants to verify that the now I'll write down the ket version of this. So remember when we were talking about orthonormal basis states, we introduced something called the completeness relation, which is the relation which states that if I take any orthonormal basis set, and I find the outer product of the basis sets with itself, so 0, outer product 0, 1, outer product 1, represented this way, this will give me the identity gate or identity matrix. Okay. And this should be true for any orthonormal basis states. So alpha and beta, if alpha and beta are orthonormal or orthogonal to each other and normalized to 1, then alpha plus beta must be equal to identity. Okay. And now I just introduced for you in the 2-qubit basis, I introduced the Z basis states, right? 0, 0, 0, 1, 1, 0, 1, 1. Therefore, we must demand that this relation is satisfied. This must be an identity gate in the 4-dimensional Hilbert space. Okay. What does that mean? Well, we can think about it from the perspective of Ket algebra, or we can think about it from the perspective of linear algebra. We introduce both perspectives. I encourage you to think about the Ket algebra version, right? Which is, we just introduced that, what we mean by these things. And now we can also do it with the linear algebra. Okay. And maybe I'll assign the Ket algebra version for you as a homework. And here I'm showing you the linear algebra version in the code. So you have that for reference there. So yeah, I mean, it's mostly, I had to write a function, basically. Obviously, the right thing to do here is not to take lists of this and write it. I should just write a function and do it in a for loop, but okay, it's fine. For this course, I don't have to stick to all the good rules of coding, right? So here is now, I verify the outer product now of the state 0, 0 with its bra, 0, 1 with its bra, 1, 0 with its bra, and 1, 1 with its bra. And I get an identity matrix in 4 dimensions. Okay. So it's just, once you define these things, now it becomes easy. Obviously, you could do it for 3 qubits as well. Same idea. Definitely, you should write function at that point and do it in a loop. Don't do it this way. You'll be sitting here writing long lists of these. Okay. Here's another exercise in your textbook. So maybe we should do this exercise now. Actually, I think the exercise asks you to write down the column and row representations of this vector, okay, which is fairly straightforward. This is C0. Okay, but maybe we'll do that first, and then this will become a little bit more clear. So let's. I know that the 4-dimensional stuff can be a little bit confusing and intimidating at first, but hopefully, if we do a couple of examples and then I show you the code, it won't be so bad. Let me keep that on till I erase it. I won't remember. Okay, so. So the state psi is equal to, oh, I already forgot. Oh, man, my memory is still. What was it? It's not really at all. For this, 1/2 0 0 plus j over 2, so I over 2, 1 0 plus root 3 plus I divided by 4, 1 1. Okay. Now I can. Okay, so if I want to write this in the linear algebra representation, then I take the 1/2, I put it on the top element because that is in front of the 0 0. 0 0 has the decimal representation 0, so that's the topmost element, right? So that's 0. And then the next one is the 1. Well, in this case, this is 2, so we don't have anything there, so this is just a 0. Okay. And then we have 2, the binary representation of 2 is 1 0, and that has I over 2. And then the last element is root 3 plus I divided by 4. Okay. So that's our column vector for psi. And then the bra vector is just that turned on its side and conjugated. So psi is just 1/2 0, and now I need to take complex conjugate of I over 2. Okay, so that's minus I over 2. And then complex conjugate of this guy is root 3 minus I. So that's our row vector psi or bra psi. Is that clear to everyone? Okay. So I just did the same thing. I wrote down this psi with the same notation here, and you can see, don't get confused by the fact it's on its side. I mean, it's for a computer, so it has to keep the representation a little easy to read, but that's basically what we just wrote. 0.5 is half, 0, 1/2 times I, and then this one is just the numerical value. And I calculated now the inner product of the bra with itself, or the psi with its bra. Okay. And you can do that. We just wrote down the bra and the psi, so I encourage you, I'm not going to sit here and try to calculate it by hand, but I encourage you to go back and verify that if you take that row vector and its column vector, and I take the inner product of the two, I need to get this number over here. Okay. And I did it by just in Python, just to make sure everything was correct. So when I do it by hand meaning I make Python do the actual explicit calculation, then I do indeed get the same answer. Okay, so any questions so far about representation in this 4-dimensional Hilbert space and column vectors and all that? Kronecker products. Okay, now let's do an example which has to do with measurement. Okay, we have talked about basis states. Now let's talk about measurements. Okay. So let's consider a state which is 1 over root 2 0 0 plus 1/2 0 1 plus root 3 over 4 1 0 plus 1/4 of 1 1. Okay. So what is the probability to measure the state of the two qubits to be in the state 0 0? What would that probability be? Given this state? Yes. 50%, 1/2, yes, okay, very good. Everybody now understand that? We take 1/√2, square it, so that's 1/2. Somebody else, what about this one? Yes,
Quarter, right?
1/4. What about this one? Yes,
3/16.
3/16. What about last? Somebody else, yes.
16.
Okay, very good. Let's add it up, right? 1/2 plus 1/4, right? That gives me 75%, right? Okay. And this is 3/16 plus 1/16, so that's 4/16. That's also 1/4. Good. So the total probability to be in one of these states is 1, right? When I add up all the probabilities. 3/4 plus 1/4 plus 3/16 plus 1/16. Everybody okay with that? Okay, but now we can ask more interesting questions with 2 qubit states. We've been thinking about what happens when we measure both qubits. But what if we didn't measure the first one of the qubits? What if we only measured one of the qubits? Okay. So the question we ask now is, what is the probability not to measure both, but to just say measure 0 on the left qubit? So you see, we want to only know those cases where we got a 0 on the left qubit. What would that be? Any thoughts? How could I go about finding
Yes.
of which two? First two. So sum the probabilities to be in this one and in this one. You see that? Because if I ignore the other qubit, if I'm ignoring that qubit, whether it's 0 or 1 doesn't matter to me, right? Then I should only take those elements in the superposition which have a left qubit giving 0, which is the first two results over here. So 1/2 plus 1/4, so 75% of the time. Okay, I'll get a 0. Okay, and we also want to know what is the probability. That's the next. We also want to know what is the state. After I finish the measurement, what will be the state of the system? This is a more interesting question, perhaps, than even just finding the probability. Well, what do you think? What is the state of the system after I measure, conditional on measurement of the first qubit to be in state 0? Anybody? Yes.
So the left qubit collapses to 0 state.
Correct.
The right qubit is still either or.
Right. So, which is it? What is the state?
Oh, so the actual state would be it would probably just be the left two.
Exactly.
Yeah.
Exactly. Very good. Yes. So the state of the system after measurement, let's just write it out. One over root 2, 0, 0, plus 1/2, 0, 1, plus root 3 over 4, 1, 0, plus 1/4. Okay. So this is our state. And as we just said, when we measure 0, we are picking out those states in the superposition where the first bit is 0. So, and we just said the probability of measuring 0 on left qubit was 1 over root 2 whole squared plus 1/2 whole squared, which is 3/4. Right? And the state that is resulting must be the state 1 over root 2, 0, 0, plus 1/2, 0, 1, because I haven't measured the second qubit. Right? So its state is still undefined, and it collapses, the state of the system collapses to only those where the first qubit is 0, and the second qubit, of course, we don't know. Okay. But now we can ask ourselves, is this state normalized for the second qubit? Okay. Is it? 1/2 plus 1/4. So it's not normalized. So we have to normalize the state. Okay. So this is, we normalize the state by the usual trick, which is we write down A times this 1 over root 2, 0, 0, plus 1 over 2, 0, 1, and we'll choose this A such that the overall probabilities add up to 1, which means we choose A squared over 2 plus A squared over 4 equals 1. Okay. All right. So that is 3/4. So which implies A equals 2 over root 2. Okay. Right? Everybody agree with that? Everybody follow these steps? Not just stop me, because these are important considerations. So we see that even though we didn't do anything to qubit 0, we have modified its state. Okay. We never touched qubit 0. The second qubit. Right? We only test the first qubit. We only measured the first qubit. But by doing so, we have changed the state of the second qubit. This is beginning to be the sort of the initialization, so to speak, initiation for you into the weirdness again of something called quantum entanglement, and we'll delve into it a little bit more. But the idea is making measurements on one thing can affect the other if the two are in something called an entangled state. And this state that we have written down happens to be an entangled state. And we'll prove all these results a little bit more in a while. Okay, but let's just keep going with our so if left qubit is 0, probability of that happening, probability left qubit is 0 equals 3/4. We calculated that. And its state, the state which then leads to the state, now I multiply out that 2 over root 3, I'm going to get root 2 over 3, I think, yes, times 0, 0, plus 1 over root 3, 0, 1. Which is correct, because now if I normalize, if I calculate, this will be 2/3 probability for the qubit to be in the 0 state, 1/3 probability for the right qubit to be in the 1 state. Okay. At this point, the state is no longer in entanglement. Well, anyway, we'll come back to entanglement. But anyway, so the point is that we have now shown that. Now let's do, what about, we said, well, what is the probability for the left qubit to be in the state 0? What about the probability for the left qubit to be in the state 1? Right? We can have that occur as well. Certain in quantum mechanics, when you measure things, nothing is certain. We can have results where now the left qubit is in the state 1. Okay. So what is the probability? Left qubit is 1. Anyone? Sure. 1/4. Correct. Because it has to be, but let's verify. So it has to be modulo squared of this plus modulo squared of that, right? Because that's the only two situations in which the left qubit is 1. So that is 316 plus 116, which is equal to 1. So good. So the left qubit can be 0 with 75% or 25%. Those two add up to 1. Now, of course, the question is, what is the state of the system after the left qubit has been projected or has been found to be in the state 1? Collapse. What is the new state of the system? After the measurement. Yes?
It's just rad 3/4, 1 0 plus 1/4 1 1.
Exactly. And again, the question is it normalized? No, right? Because if I, as we just said, if we take the squares of these, that gives me 1/4, doesn't give me 1. So for an appropriate for the qubit state to be normalized, I have to now multiply again by some constant b. So I multiply by a constant b times 3/4 0 plus 1/4 1. And now I demand that b times 3/4 16 plus, so this gives me, so the demand is mod b squared times 3/16 plus 1/16 must be equal to 1, right? So b squared is equal to 4, and therefore b equals 1 or 2. Okay, so I have to multiply by 2 and keep this over here. Erase that. So I need to multiply this, or maybe I'll just write it here. Okay. So I'm taking that 2, multiplying it out. This is √3/2 times 0 plus 1/2 times. Again, we can verify now the probability for the, oh, sorry. I should include the left qubit. Even though I measured it out, we want to keep it there in the state so that we know the left qubit is in the state 1. Okay. So now the probability for the right qubit to be in the state 0 is 3/4. For the right qubit to be in the state 1 is 1/4. So again, it normalizes out to 1. Sum of those two. Everybody following this example? Okay, so basically this example, as I said, kind of gives you a sense of why it is that when qubits are in this joint superposition state, reading out one can affect the other. Okay. But of course, reading out is a very destructive sort of operation. We're collapsing the state of the system. And that makes it, obviously change what the other qubit is in, but that's an interesting effect in and of itself. But we'll now come to things that allow us to more gently manipulate the states as well. Okay. How much time? Not much. Let me just finish up with a couple last marks, I think. And we'll be done. Okay, we've just gone through all these cases. So what is the probability to measure 0 on the left qubit? We just did that. And what is the state after measurement? What is the probability to measure 1 on the left qubit and the state after measurement? We did that. Okay, now I want you as an exercise on your own, and we'll discuss these results in the next class. Calculate the probability to measure 0 on the right qubit and write down the state after measurement. Okay. And also, of course, what is the probability to measure 1 on the right qubit and what is the state after measurement? I encourage you to work this out yourself by hand. Don't cheat and look and make sure that this all makes sense to you. And I think for today, that will be the last slide. I think. Yeah, I think we have more qubits, but I'll just get to that in the next class. Okay, so, oh, sorry, I removed the slide. Anyway, that's it for today. The summary for today is we discussed n-qubit states, we discussed the Kronecker product, which allows us to generalize to multi-qubit systems, and the single qubit measurements. We've gone through a few of these cases. And we'll discuss the experiments. Okay.